So, good morning, everyone, and welcome to this first session on the doctoral meetings. Sorry, there's a mistake here. In this track, we're going to be hearing about 4 PhD students working on computational and experimental aerodynamics. And they are Yungwei Chen, who will be talking about his thesis on data-driven flow measurements. Exan Frasanmik, who will be talking about statistical learning tools for turbulent flow control. Jacopo Tirelli, who will be talking about his thesis on data-driven enhancement of optical measurement techniques. So 3 theses on experimental fluid dynamics, mixing data-driven techniques, and trying to characterize flows. So very interesting talks. And then Juanma Catalan, who will be talking about his thesis on unsteady aerodynamics of flapping wing micro-air vehicles. This is a more numerical aerodynamics thesis. So thanks very much for being here. And now I hand over to Yungwei Chen for his presentation. Thanks very much. There will be, by the way, PhD students will be delivering a presentation in 10-15 minutes, and then there will be a round of questions.
Hello.
So go ahead, Yungwei.
Yes. Let me share my screen. Hello, my topic is about data-driven flow measurement. In order to find a complete flow description from the combination of incomplete measurements, and here is a simulation about wing. You can see there are many 3-dimensional flow structure on the wing. So if we use a point measurement or 2-dimensional measurement on that, we cannot find the full information of the flow field. Oh, here is a picture about Asian Indian story. Some people close their eyes to touch an elephant. They may touch its nose and think the elephant is a rope, or they may touch its hair and think the elephant is a fan, but it's not exact what the elephant. And here is a famous picture about the development of flow measurement. We used to have a single point measurement, but there are not much information. And with the development of technology, we have more and more dimension in the measurement and more and more component. And with the high-speed Tomo PIV to measure the 3-dimensional velocity, we can calculate the pressure from Navier-Stokes equation. So we have the four-dimensional and 4-component complete description of the flow. But the rejection of high-speed measurement is that we need high-speed laser and cameras, and there are 2 kinds of laser frequently used in PIV. One is NDYYG, another is NDYLF. The high-speed laser NDYLF has a higher sample rate, but it is expensive, and the average cost power of NDYLF is lower, and they need high-speed cameras, but such cameras are less sensitive, and even we have the laser and cameras in the highest speed, they can only measure for low speed flows. So there are many shortcomings of the direct high-speed PIV. And for the measurement of pressure, we can use the exact velocity, 3D velocity, and the Navier-Stokes equation to find the gradient of pressure and integrated it into the real pressure. And for the left for the lower speed PIV, the time resolved item of the Navier-Stokes equation is not easy to know. So there are some ways to find it. One is using the continuity equation, so that the time derivative will be removed. But but in this method, the time derivative of pressure of, of velocity is still need to know on the boundary. So we need full boundary condition. Another way is to make use of Taylor's hypothesis, but it cannot endure for a long time. And another way is use the vortex in cell method. However, it is not endurable in time, and it do not consider dissipation. So we want to take the advantage of data-driven techniques by exploiting combination of incomplete measurements to obtain a complete flow description. And there are several ways to achieve it, such as ePort, KNN, and CNN. And here is the first case we use to validate our method. Here are three fixed current cylinders in the flow, and we measure the wake. We measure the wake, and there are 5 probes here, and the velocity on the probes is also recorded, and we can use the high sample rate probe data and some snapshots to reconstruct the time-resolved flow field, and using the Navier-Stokes equation to calculate the pressure. And here is the method of ePort. We use the POD, proper orthogonal decomposition, to decompose the flow field into the temporal modes, singular value, and spatial modes. And for the probe data, we also do it, and we can find the correlation of temporal modes between the fields and probe data. Then we have another time-resolved probe data, so that we can reconstruct a time-resolved flow field. And here is some result. The first column is the pressure and the velocity from the simulation, and the second column is the pressure and the velocity. We use ePort to reconstruct it, and with the proper filter in the ePort, we can get better result. As you can see, without filter in the ePort, the time derivative of the velocity is not good. So that they this method get not good pressure, but with this filter we just find recently, we can get very good result. And here is the conclusion. The data-driven measurement in the simulation of pinball flow works well, and with the suitable filter, the accuracy of ePort improved, and we can get very accurate pressure estimation from the new method. And what we are doing next is to improve the method and validate again and again to find the to improve the method, and then we can find some application of this method, such as estimate unsteady force or identify the noise source. And I just started the PhD 2 months ago, so there are a lot of work to do later. And thanks to the European Research Council.